Okay, let's get started, please. So, remember what we were talking about? We are defining the volumes of solids, right? And the idea is that, you have, we had, our last example was something like this, right? You have some object, right? And it's, you're able to find the surface area for each x. You have some way of figuring out the surface area of a slice of that object, right? So you cut through the object at a particular time, right? And you figure out what the area of the cross section is, right? So A of x is the area of cross section at position x. Right, and what you do is you think, well, I'm going to take, you chop this thing into. You chop this thing into, a certain number of subintervals, and let's call these things x0, x1, x2, x3 to xn, right? And you say, okay, I'm going to take a at x1, right? I'm going to take the area of that cross section at x1, and I'm going to multiply it by the width. So make each of these things delta x in width, right? Delta x is going to be b minus a over n, right? And you say, okay, I'm going to take a x of 1 times delta x, and that will give me an approximation of this first volume, right? That'll give me an approximation of this first volume, and then I say, and then you add on a at x2 delta x, right? And that'll give you an approximation of the second volume, and so on and so forth. Then you add all those things together, right? Add all these things together, you get axi delta x as I goes from 1 to n, right? Which is an approximation of the volume. Right? This thing's the approximation of the volume, and then you let n go to infinity, right? Let n go to infinity, and you say, well, look, this is the Riemann sum. This is the Riemann sum for a definite integral, right? This is the Riemann sum for a definite integral. What's the definite integral? It's this one, right? Ax delta ax dx, right? Right. And so this is what we call the volume. So that's how we figure out the volume. That's the idea. And we did some example of this last time. Okay. Everybody okay on the idea? Everybody okay on the idea? Right? Right. You do some approximation. You say, well, as n goes to infinity, this actually turns into a definite integral. So that's what we're going to use. Okay. Some people like to think of this as this dx as some sort of infinitesimal width. Infinitesimal width. Right? You have your object, right? And you think of you have your ax. You have this area, and you multiply it by some sort of infinitesimal width, right? Some sort of width that's smaller than any number, right? And you get the volume of a very thin slice, right? And then you add up all these volumes together, and then that's the total volume. Okay. But okay, what does that mean in infinitesimal? Right? It doesn't really mean anything. So it's probably better to think of it in terms of Riemann subsets. But actually, when Newton created calculus, he thought of things as he thought of these infinitesimal things. So it's not a bad way of thinking, but it's just sort of hard to make mathematically sound. Hard to make mathematically sound, because what does it mean to have something that is, the thickness of it would have to be smaller than any positive number, but bigger than 0. Right? Smaller than any positive number, but bigger than 0. Well, what does that mean? In our number system, that doesn't mean anything. Right? Okay. Let me see if you can try. So I have one hard one left from last time, and I want you to try it. So here's an exercise for you to try. So here it is. You take a right cylinder. So you take a circular cylinder, and it is of radius 3. Okay. Circular cylinder of radius 3. You cut it in half. Okay, you cut it in half. Okay, and then from this cut here, you extend the plane at 45 degrees upwards from there. Okay, so you slice a plane through it, and you chop off this thing here. Okay, you guys see what I'm saying? So you take a cylinder, you cut it in half. Okay, cut it in half, and then from this line at the base here, you extend the plane at 45 degrees upwards. Okay, and you chop off this little wedge. This, I don't know how to draw it, something like this. You chop off this. That's not right. You chop off this thing. Just have a plane here coming up at 45 degrees, and you chop off this little wedge here at the bottom. Okay. And I'd like to know the volume of that wedge. So remember that the radius is 3 here. Okay. So from the side, right? If we turn it from the side, it'll look like this. Oops, 45 degrees. It'll look like this. Right? Like we cut from the side, the cylinder looks like this. Right? Looks like this. We cut the thing in half, and then we cut a plane up at 45 degrees. Okay, we cut a plane up at 45 degrees, and we've got this little corner piece here. Okay, and I'd like to know the volume of that corner piece. somebody nearby, please.
Adding up all the slices that a half circle and they're slowly getting smaller so you can find an equation. Yeah. Radius is yeah. Okay, did you get to an equation?
Oh, I see what you're saying.
You know how we did in class, like as this something?
Yeah.
That's what I was doing, is you add up all the half circles and you can just all of that from
Yeah, I had the radius to calculate, but I didn't. You're right.
doing how to do the radius also work.
Well, yeah. So that makes sense. So the radius starts out at 3. It's going to be over a height of 3. So I did 3 minus x. Yeah, exactly. That would be it.
X is approaching 3, right?
Yeah.
Okay. Anybody want to say anything about this? Like how you would slice it? How you're going to? How did anybody slice it figure out?
Well, I think it's better to do with dy method, the thickness. That's what I was thinking. Chandler and I.
So you're going to I see.
Make it like a bunch of I guess concentric circles. They start at the bottom. The very bottom one obviously is radius 1.5, and then going up, the thickness is dy, the infinitesimal amount, I guess. So we're working on how to figure distance x there for the radius.
I'm not following. Do you mean to say that you were slicing this way?
Yes, exactly.
You're slicing this way?
Yeah.
Okay. Okay. So right, the radius is 3, right? The radius is 3. So what do you set up?
Well, what I had was 5x squared dy, and that's where I got stuck, because now I'm going to change. So we're working on changing the x in terms of y.
Pi x squared dy.
Yeah, x squared meaning representing the radius from the origin of every single circle.
Well,
And then I have to subtract the line they go 45 degrees.
yeah. So
The x minus. Okay, well.
okay. So that did anybody slice it the other way? Anybody try to slice it this way? Let me show you how I did it. So I said, okay, let's take an x, right? X ranges from 0 to 3, right? If you cut through here, then what kind of an object do you get? What kind of a cross section do you get? So right, I'm going to cut. I have my cylinder right here, right? And I'm going to cut it like this, right? I'm going to cut it like this. That is, I'm going to cut like this, right?
Yeah.
Right. It actually be a rectangle, right?
Yeah.
It's going to be a rectangle because the sides of the cylinder are straight up, right? The sides of the cylinder are straight up, and you're going to have this line going across here. Same thing, line cutting across on the bottom. Okay. So then we want to figure out a of x, right? Right? We want to figure out a of x. Well, you say, okay, I need to know I need to know here's my rectangle, right? I need to know the height at time x. I also need to know the width at time x, right? Okay. Well, what's the height gonna be? At time x, the height's gonna be, what's the height? Don't blurt it out, please. Don't blurt it out. Yeah, but it'll be x, right? Because you've got a 45-degree angle here, right? So if this is x, then certainly this is also going to be x, right? Okay. Now, take 30 seconds and see if you can figure out the width. Let's look at this thing from the top, right? It's a circle of radius 3, okay? It's a circle of radius 3, so you know that, x squared plus y squared is equal to 9, right? If we're cutting at time x, well then, what's the width of that rectangle? If this is x, this is y, right? Right? So the width of the rectangle is going to be 2y, right? 2 times y, where y is going to be the square root of 9 minus x squared. You guys see that? Right. This point xy has to satisfy x squared plus y squared equals 9, right? So y is going to be positive the square root of 9 minus x squared. And the width of that rectangle is going to be just twice that, right? As x, at the very beginning, you get 3, and as x increases, then y shrinks down to 0.
Why does that equal 9? Sorry, why does that equal 9?
Because this is a circle of radius 3, right? So this is saying that the distance is 3. The distance to the origin is 3, right? If you you're saying that x minus 0 squared plus y minus 0 squared square rooted is equal to 3. Right? This is, you remember the distance formula? Right? So this is saying that the distance of xy to 0 to 0 is 3. Right? What's a circle? It means that a circle radius 3 means around the origin means that every point has distance 3 to the origin. Right? So use the distance formula. Well, that's the same thing as this, u squared. Okay. So the area, right? What's the area going to be? Well, a of x is going to be x, the height, times the width, right? Times the width, and we're going to integrate that between 0 and 3, right? So the volume is going to be the integral from 0 to 3 of twice x, the square root of 9 minus x squared dx. sure you could do it the other way as well, but I think it'll be much harder. I think it'll be much harder, at least some, a little bit harder.
You have to subtract, it's a little bit,
You can definitely do it that way, but I don't want to. What? Yes. Okay, anyway, so this was maybe the trickiest one we've shown you, but the moral is still the same, right? To find the volume, you need to find the area of the cross section, right? This one involved a little bit of geometry, but you know, it's not, you know, once you figure out the area of the cross section, just you integrate that over the range of integration. Is that all right? Everybody okay? Okay, so let's go on to the next idea, which is volumes of what are called solids of revolution. Solids of revolution. Okay, so this is when you have a very specific kind of solid. And it's this. You have some sort of function between A and B. Okay. And you basically create a solid by taking that area and then rotating it around an axis. Okay. So we're going to take that thing and we're going to rotate it. We're going to rotate it around an axis, right? Okay, and we get a solid object. Okay, so imagine that your solid is obtained by taking this curve and then just rotating it around, and that's what your solid is. Okay, right? In that case, getting the area of the cross section is easy. Right? If this is time x, and I cut through at time x, well, what's the area of that cross section? It's a circle, right? It's a circle, so it's going to be pi r squared. Well, what's r? R is f of x, right? Y, or f of x, right? So you get pi r squared. Right, and so the volume is just going to be the area, the integral of that, right? Pi r squared dx. Okay, and you could do something similar to this. If you had something like this, where you had a function x was some function of y, right, between c and b, and you took that thing and rotated it around, right? Then you have this exactly the same thing, just go vertically, right? So the area here, the area of each slice, right? So you'd say, well, at a fixed height y, my area is going to be pi r squared, right? And so the volume is going to be the integral from c to d of pi r of the area d1 against dy. Okay, it's exactly the same thing. Yes, Chandler.
When we take the area of that object right there, is that like the same thing as taking like the sum of like first sums?
The sum of what?
I don't know, the term like first sum, I think, like
First sums?
first sums or something.
First sums?
Yeah. If we divided that object we have into like infinitesimally like straight lines, and like I believe those are considered first sums.
Yeah. So frustum is basically like a truncated cone,
Right.
right? You've got this cone, and then you chop it off. Yeah. So, I mean, that will result in the same thing.
Okay.
Yeah, you could think of it that way. But the way we're actually thinking of it is we're sampling at different points. We're sampling at different points, and then we're taking actually discs. Actually taking discs rather than guys with slanted edges. So my discs have perpendicular edges, right? Or they have perfectly horizontal edges, right? They're like this. Okay, they're like this, rather than something like this. Okay. Okay. Yeah, so, but it'll end up with the same answer. Yeah. Okay. Okay, so let me just give you a simple example. If I have, my function is the square root of the cosine, right? So it looks something like this. Okay, where x ranges from 0 to pi over 2, right? And I want to take this object and I'm going to rotate it around the x-axis. Okay, I rotate this thing around the x-axis and I get some sort of weird-looking object here. Take 30 seconds and write down a formula for the volume. Okay, so what is it? It's too easy. What is it? Somebody tell me. Daddy?
It said the integral from 0 to pi root of I cosine x dx.
Yeah, exactly. Pi cosine x dx. You just take the radius, right? This thing is the radius. You square it. Pi r squared times pi r squared dx integrated between 0 and pi r. Simple enough. Let me do one that's maybe a little bit more interesting, which is you take the parabola y equals x squared, and you take the line y equals 2x, and you get this thing here. Okay. You get this thing, and I'd like you to rotate that around the y-axis. Okay. And so you get this kind of cup. Okay. And I want you to find the volume. Write down something for the volume of that cup. Y equals x squared is the parabola, right?
Oh.
And then y equals 2x is the line. we want the volume of the cup that you get when you rotate the kind of peculiar cup you get when you rotate this thing around, right? Right. So let me say how we're going to do it. You want the area of the cross section when you cut it at a particular height. Right? So cut it at a particular height y, you're going to get a cross section. Well, what does a cross section look like? Circle. It's a circle with a smaller circle removed from it, right? Right. It is the object that you get when you take this little band and you spin it around the y-axis, right? Right. This one's called an annulus in math language. Maybe a ring in normal language. It's often called a washer. Right? Washer, as in the thing you use when you screws bolts and stuff. Okay, talk to somebody nearby.
Exactly, yeah. Yeah, so would it be
Like
y divided by 2? Yeah.
Yeah, y over 2. So you have to have this one on the outside, right? You have square root of y
Yeah, right.
minus one on the inside, which will be y over 2. And then right here, when you square it, you can square before you subtract.
Or I think actually,
I forgot to do. And then you can multiply it.
hold on, maybe we found a circle of using the x. Yeah. So it'd be like 2x pi 2x squared, which is the outer circle, minus, I don't know this. Yeah.
Okay,
Because-
let's talk. So, what's the area of the cross section? How do we figure out the area of the cross section? Well, how do you figure out the area of the cross section? Well, yeah, Elizabeth.
Oh, I just said outer minus in.
Sure, right? So you say, well, pi of the bigger radius at height y minus pi of the pi squared minus pi of the smaller radius squared, right? Right. That's going to be the area at height y. Right. You get the area of the big circle, and you subtract off the area of the little circle, right? Where let's call this inner radius little r, outer radius big R. Well, what's big R? What's big R? If this height is y, what's the x value here? Right? We want the x value, so it's going to be x is going to be x squared. No, x is going to be the square root of y. Thank you. X is going to be the square root of y, right? So big radius is the square root of y. What about the small radius? Right, at height y, x is going to be y over 2. Little radius is y over 2, right? And so you end up with pi big radius squared minus pi little radius squared. Okay. And of course, you notice that you could have written it as pi big radius squared right? Pi big radius squared minus little radius squared. If you wanted to, which is cleaner. Yes?
Oh, sorry, I just missed how you got the square root of y and y equal to.
Sure. So you think, okay, I'm at height y right now. Well, the parabola is y equals x squared, right? My radius is going to be my x value. My radius is my x value. Well, if my height is y, and I know that x squared is y, then my x value must be the square root of y, right? So x must be the square root of, x must be the square root of y here, and over here x is going to be y by 2, right? Because y is 2x, so x is y by 2, right? If my y is fixed, well, my x is half of that y. Okay, so then you take that and you integrate it. So you get the integral from what to what? To 0 to 4. Right? You see where those guys intersect, right? They intersect at 2 comma 4, right? So the y's range from 0 to 4. So the volume is going to be the integral from 0 to 4 of this thing, pi y minus y squared over 4. Whoops. And that'll be the volume of your odd-looking cup. And of course, you could have done this in 2 pieces if you felt like it. Right? You could have said, I'm going to take the area, the volume of that parabolic nose, right, and then subtract off the volume of the cone. Right? You could have done it that way. Oh, it's the same thing, right? You would get, this. You would get this thing minus this thing. Right? The area of the parabolic nose minus the area of the cone. I'm sorry, the volume of the nose minus the volume of the cone. Right? It would be the same thing. Okay, but most people do it in one move, and this is called the method. It's given a name, the method of washers. Method of washers, or the method of discs. However you spell discs. Yes. I'm not sure why, but a lot of people spell it with a C in math books. Strange. Okay. Everybody okay? Right. Get the area of the cross section. Right. The cross section is this washer. Well, the area of the washer is just the pi big R squared minus pi little r squared. Okay. So let me give you one last one. It's this. You have a parabola, y equals 3x minus x squared. Okay. If you look at this guy, you see that it intersects at 0 and it intersects at 3, right? Because when you factor out the x, you get 3 minus x. Right? Intersects at 0, intersects at 3, it's downwards parabola. So take the area under that parabola and above the x-axis and rotate it around the line of x equals -1. Okay. So you get this fun cake. And I'd like to know the area of the volume of the cake. Okay. But I think we'll leave this for the beginning next time. So let's start off with this. Next time, Right now, let me return the exams.